Happy snow day, everybody. February 12th, 2019. I hope you're enjoying your time at home, maybe with a cup of hot cocoa or and a good book, or on your computer listening to physics lectures. So I want to take a minute and quickly review the types of energy we've talked about. So remember, the first thing that we learned is that work is force times displacement. So work can be a vector because you can have work being added to something or something doing work on another object. This is just one of the first ideas we have considered this unit. And then we use the work equation to help us derive the elastic energy. So remember, this came from spring potential, and if you take, remember this was a force versus displacement graph, and it would produce us the area under the curve. Since it's a triangle, that's 1/2 of F times delta X. And in our case, the K value is the spring constant, so that tells us the slope of the line. So we can really substitute, the force applied by this on the spring for the force of work. And anyway, this is how we got to the elastic energy equation. The other equation we have derived so far was the kinetic energy equation. So kinetic energy was 1/2 mv squared. And remember that we used another pretty lengthy derivation using the Torricelli equation. We ultimately substituted for work. We used m times its acceleration, and acceleration equal to 2 delta x. So overall, anyway, we were able to get to this idea. The derivation for the third type of energy is much simpler and straightforward. We have mass times gravitational pull times the height. And so I hope that this is a little bit more straightforward and you can see how energy can be stored gravitationally by supplying work. So if we have the Earth, and on the Earth we have a box, and let's make the box 1 kilogram just to make it easy to do some calculations. If we do work on the box, so a person comes over and they pick up the box and they lift it. So this person holds the 1 kilogram box 1 meter off of the ground. If we consider the lifting of the box from the perspective of work, let's recall that work is the force times the displacement. So in order to overcome the force of gravity, you have to at least supply that amount of force. So in our case, because it's a 1 kilogram box, that's 1 kilogram, that's the mass, times the gravitational constant, which is 9.8 newtons per kilogram. And since we lifted it 1 meter, we're going to multiply that by 1 meter. So this calculation is pretty easy. The kilograms cancel, and we're left with 9.8 newtons times a meter, which, if you remember, is a joule. So you can supply 9.8 joules of energy to this box, and it comes from the biochemical energy stored in the person as they ate food, and that's converted into ATP. The ATP is then used to activate the muscles, which use their actin and myosin filaments to pull. It doesn't matter. All of that stuff is conserved. You eat food, helps you lift. So by changing that energy into gravitational energy, you now have 9.8 joules of energy stored in the box, and in reality, it's stored in the space between the box and the Earth. So, we said that the energy is stored in the gravitational field. That's where it's stored. It's stored in the gravitational field between the Earth and the box. So if we look at this scenario using the same sort of thinking, let's take a big building. We'll make it MUHS, and we'll put a box on the very top. And we'll say that this is 20 meters high. And at the very beginning, it's not moving. Okay. And then somewhere in the middle, we'll use the box. And now it's like falling down. And it's like halfway in between. So the height of this is 10 meters. So let's make the box the same again. So a 1 kilogram box. And then lastly, let's consider a situation where the box is moving like as fast as it can possibly move. So this is much greater than 0. Oh, here, the velocity is greater than 0. And basically, it's just about to hit the ground. It hasn't quite yet, so height equals 0. So if we thought about this from the work perspective, we've added 20 meters of height, or the distance is 20 meters. We've added 20 meters of distance. The mass is 1 kilogram, and the gravitational constant is 9.8. So if you add that much work, that means that you have energy stored in the gravitational field. So the gravitational equation is m times g times h. So if our m is 1 kilogram and our g is 9.8 newtons per kilogram and the height is 20 meters, this means that we have 490 joules of energy stored in this gravitational field between the box and the Earth. In the middle, if we think about the gravitational energy, we only have 10 meters, so we have 1 kilogram times the 9.8 newtons per kilogram times 10 now. So in this case, 10 times 9.8 times 1 is 98. Oh my goodness. It's a big mistake. Sorry. 20 times 9.8 is 196 joules. 20, not 50. Okay, so to recap, at the very beginning, we have 196 joules of gravitational energy stored in the gravitational field between the box and the Earth. In the middle, we only have 98 joules of energy because we have half the height, so we have half the energy. At the end, our gravitational energy at the very end is 1 kilogram times 9.8 newtons per kilogram times 0, which is 0. So none of the energy exists gravitationally. So again, in class this week, we've kind of started talking about these little bar charts. And so this circle, this represents the thing we're talking about. So the system, in this case, the system is the box. All right, so in the very beginning scenario, all of the energy exists as gravitational energy. All of the energy stored in this gravitational field is associated with the box. No, there's no other kinds of energy that it's being stored as. So if we think about the other two questions, is the box moving? And it's not at the beginning. It says the velocity equals 0. So that means that your kinetic energy is 0. The other question is, like, can it be sprung? And it cannot. There's no spring. There's no, like, rubber band or elastic that's, like, determining or, like, preparing to launch. So that's also a 0. So in the middle, the gravitational energy is now half as much. So if we use these imaginary boxes to like qualify how much energy we have, we know that there is only half as much energy that exists stored in the gravitational field. So where did the rest of that energy go? Well, now that it's moving, and because we know that energy is conserved because of the law of conservation of energy, the rest of the energy must have been converted into kinetic energy. And finally, if the height is 0, that means that the final gravitational energy is 0. So the only energy that remains is stored in the motion of the object. So we call that the total energy has transferred into kinetic energy. So if we're thinking about our kinetic equation, 1/2 mv squared, we know that all of the energy, so since we started with 196 joules, we have to end with 196 joules. And since we know that the mass of the object is 1, we know that if the question is something like how fast is the object going an instant before it hits the ground, due to the total conservation of energy from the beginning, 196 joules equals 1/2 mv squared. So this is something that we would be able to solve for. Multiply by 2, divide by 1, take the square root. Okay, that's it. I hope you enjoyed your snow day. If you have any questions, feel free to email me. We will do the Hooke's Law quiz in class on Wednesday. Otherwise, good luck completing worksheet 3.